All right, so test a week from today. I'll have a review on Wednesday, but first off, is a week from today okay? No major conflicts. Again, I don't want to test your ability to go without sleep, so...
Maybe answers open Thursday night?
Wait a minute, that's like 4 days ahead of time.
Do you want to go on the weekend and start posting stuff on your Saturday?
I'm happy to post something on Saturday.
I'm just saying, there's better uses of your time. Might as well do it during the week when you're working anyway.
It's 5 seconds. It's not really that hard to do. Just have to put a reminder on my calendar and I'll do it. All right, so we're good with the test on Monday, and it's up to today. So today's the last lecture. We'll have a review on Wednesday to talk over everything in total. Yes?
Michael Mills' course also has an exam that morning. Would it be a nuisance to the schedule if you moved it to Wednesday? If not,
I have a vote for Wednesday. Any conflicts?
like next Wednesday. Yeah.
This coming, not this Wednesday, but a week from Wednesday.
So like 2 days after when it's supposed to be, because we have another class of exam.
Yeah, we got a couple votes for yes, but are there any conflicts?
Are we raising our hands in agreement with Wednesday?
You're raising your hands.
Thumbs up for Monday, thumbs down for
No.
Wednesday.
Tell me if you have a conflict with a week from Wednesday. That's what I'm looking for. I don't want to inconvenience a larger group of people. Okay, so it's Wednesday next week rather than Monday next week, which means I can post it on Monday, right? Okay. All right. Okie dokes.
Thank you.
You're welcome. Not a problem. All right. Anything else that we still need to resolve? We're good to go? All right.
It's still up to today.
Yes, today's lecture only. Yeah.
So it's 20th and 27th?
Yeah, I think so. We'll cover that on Wednesday. I'll give you the review. Okay. All right, so today we're going to talk about polymer solutions and some aspects of how we describe polymer solutions, some of which is starting off here is going to be pretty familiar to you. And then we get into some predictive aspects of polymer solutions, meaning what polymer will dissolve in which solvent. And we've talked about like dissolves like, and we're going to talk a lot more about that today and the limits of like dissolves like, but go through some quantitative methods of predicting solubility that you guys will become familiar with. It's nothing too difficult, it's just a matter of paying attention to the rules. But first off, we'll talk about polymer solutions and the act of dissolution itself. And so first off, we want to define how does a polymer dissolve, and of course, again, like dissolves like is still important here. So let me just write it down because it still helps us understand what's going on with these systems and what to expect. And it's bugging me the other day. Someday I'll go through and say, okay, here's what like dissolves like actually means. But we're not going to do that this year because it's more complicated. Anyway, but in general, we think about that as still being relevant. And of course, we still have 3 different steps involved here, which is the solvent fully wets the polymer, i.e. it has to get to it and interact with it and cause a process of dissolution to be triggered. And then we have solvent diffusion into the polymer, causing swelling of the material. And so, as you recall, the cartoons we talked about how we have the interface and the solvent molecules start going in, the polymer chains start coming out, and at some point when that chain fully leaves the interface, it's actually dissolved. Until that happens, it's not actually dissolved. So it's just getting to that point. So this is very different from salt and water, in which we have ions just leaping out of the matrix. With polymer chains, it's not that simple and certainly not that quick either. And so eventually, though, the polymer chains diffuse out of the swollen mass into the solvent, completing the solvation process. And so the cartoon version of this is we start with something that is a mass of polymer chains, all of which are tightly packed together. And then what happens is, going with the previous image, we have solvent out here itching to get in there and do something. And so eventually that happens, and we end up with solvent molecules starting to intersperse with those polymer chains. And this is not to suggest it's one solvent molecule. All right, these are more than likely regions of solvent molecules. And so there's this penetration process that begins the overall process, driven by the fact that all these polymer chains want to be in the solvent on an entropic basis. Okay, So that should make absolute sense to you, knowing how entropy drives everything with polymers. Bless you. Yeah. The other thing is temperature, and I wanted to touch on this again because temperature is motion, all right, and temperature is also energy. I'm thinking of some of the answers I got in these tests, and so you think of motion before you think of energy. Okay, all right. So we have when a polymer is hot, change moving faster. And a polymer is cold, change moving slower. All right, and that's kind of the driving force for a lot of everything. Don't focus so much on what the energy of the polymer is. And so that's part of this process as well. A hotter chain will obviously go through these steps more quickly than a colder chain. And later on we'll talk about glass transition and how the effects that has. But the polymer chains are still always moving right down to 0 degrees Kelvin. Okay, so they're always moving unless you take all their energy away. Even below glass transition, they can still dissolve, which we'll talk about later. But glass transition doesn't mean they can't move, period. And then ultimately what we have are these individual coils separated from each other, of course depending on exactly how much polymer is involved. But this is what we're looking for when we're trying to crystallize these polymers, is to isolate them. In most cases we don't need to get to that level of separation, but that's the general thought. And at that point, of course, they still have lots of solvent molecules interspersed within those chains. So that's all part and parcel of the active dissolution. So all of this should be familiar to you. The entropic forces should be familiar to you. And of course, we'll talk about the fact that there's an enthalpic driver here as well, because that there always is for these different types of systems. Are any questions about all that? Should be review. Okay. And so the first step is the process of solvent diffusion into the polymer. That everything else follows from that. If that doesn't happen, dissolution can't happen. So we put water on top of polystyrene, it just sits there. It doesn't dissolve into the polystyrene, which is good because we use polystyrene to handle water all the time. All right, so we like that about polystyrene and water. And for another example, if we have polyvinyl alcohol, which I talk about a lot, we'll talk about more, we put water on top of polyvinyl alcohol and it starts to go in. All right, it's because polyvinyl alcohol has all those OH groups along the chain. Those of you who remember that structure, it's just OHs intermittently spaced on the chain, and the water can basically hydrogen bond with all those OH groups and just start making its way into the structure following the chain of OH groups. Okay, so that should make sense. And we'll talk about this some more. Molecular weight is important, and temperature, of course, I just talked about, but molecular weight is also significant. And so it's not at all unusual to have a polymer chain that, say, 10,000 molecular weight dissolves just fine. This is true of polyvinyl alcohol for that matter. 10,000 molecular weight polyvinyl alcohol will dissolve easily in water. 100,000, not as easy. All right, and so like dissolves like, but like dissolving like has to deal with the size of the chain and how difficult it is to move that chain. All right, so you might swell the polyvinyl alcohol, but the chains might be too big to come out unless you really push them. And we'll talk about that as well. All right, so both temperature and the size of the chain are important. Of course, if it's cross-linked, then you're probably not going to dissolve it at all if you cross-link it. But molecular weight and how big and how heavy those chains are is going to be important. So if we have a high molecular weight polymer, a high level of molecular interaction is necessary, meaning that it has to be able to reach in, and not just the segment that's exposed to the solution polymer interface has to come out, excuse me, but everything else, the entire chain has to come out. All right, so it's like polymers being drawn into the active zone, but even worse because it's even a longer distance to travel. So that, as says here, can require extended times to get solvent penetration, and of course all diffusion-based processes will be slower. It doesn't mean that the polymer is immune to the solvent. It turns into like a jelly substance, which means you can't rely on it to bear load or resist friction or do anything really, except if you're making hydrogels or something like that. But it does mean it doesn't actually dissolve. Is there a question, Kevin?
Yeah. So why can't these chains ever just break? I know like the carbon carbons aren't easy to do that, but I thought if like when some of these like these metal groups, that would be relatively easier to break apart. Like.
No, you'd have to be working with really strong acid. I'm not sure that a base would even do it, but there are some acids like boiling sulfuric acid that will start breaking some of those bonds. But when we talk about dissolving with organic-based solvents, no, it's not. You're not going to do that.
Just gotta untangle the chains.
Just gotta untangle the chains. That's right. All right. Any other questions? We're fully aware of the difference between breaking secondary bonds, which instantly reform, and breaking primary chemical bonds, which doesn't happen for the most part, unless I tell you it does. Okay, keep that in mind. That's what's happening here, is that those solvent molecules are going in and getting in between the secondary bonding. They're not breaking any chains, though. They're breaking lots of secondary bonds, and they sit in between polymer chains. Thus, it becomes a secondary bond between the polymer and the solvent, instead of the polymer-polymer secondary bonding. Okay, but it's still secondary bonds which come and go, blink in and out of existence all the time. And it shouldn't be a huge surprise as part of this process is these are all accelerated with the temperature increases. As the polymer chains are moving faster, the solvent molecules are moving faster, they have more energy, they can get involved with polymer chain bonding much more easily. This increased mobility means that diffusion is going to be much faster, both in terms of the chains getting out of the way of the solvent, also in terms of the polymer being attacked by the solvent itself. Just kinetically, it makes sense, aided by the fact that these chains are more mobile. And so this process of going from A to B to C, increased temperature is going to increase these processes. And as I've already discussed, and we'll talk about it again, sometimes this is necessary. And we've fought this fight in the lab a number of times when we're trying to electrospin a certain polymer, and it doesn't want to dissolve. And so we, according to what you read in the papers, it's, it should dissolve. It's like, no, it's not dissolving. So we go back to the lab and we heat it up, the solvent to 50 degrees centigrade or maybe 60 degrees centigrade, and try to get the polymer dissolved. Sometimes that works. All right, it takes a little more energy to convince the polymer that it should dissolve, as the literature predicts sometimes. All right, any questions about all that? Should be pretty straightforward stuff. All right, and then we get into some aspects of this which are significant. I wouldn't say they're dramatically important, but in many cases this can have an influence. It's probably more important in terms of biodegradation than it is in salvation, but it should make some sense that these are significant. So the amorphous versus the crystalline state. It should make sense that if you have an amorphous state versus a crystalline state, solubility should be different, right? In order to get the polymer chains out of the crystalline state, you essentially need to melt them, all right? So it requires more energy to overcome that enthalpy of melting, whereas an amorphous polymer chain, there's no enthalpy of melting associated with that amorphous chain. It's already melted, according to the physicists. So if a polymer is amorphous and the dissolution temperature is above the polymer's Tg, the rate of dissolution is high. Should make sense. It doesn't mean that it won't dissolve below Tg, but it's easier when it's above Tg. The chains in amorphous polymer are not packed in an orderly manner, can move freely when the temperature is above the glass transition. When the temperature is below the glass transition, the polymer chains are frozen, which I hate this word even more in the context of this discussion, because it doesn't mean they're truly frozen. All right, they're just more restricted. All right, they're only truly frozen at 0 degrees Kelvin. That's the only truly frozen state of polymer chains. They're always mobile. They're always moving, even above the temperatures like 1 degree Kelvin. They're still moving around a little bit. Not that solvents can do anything at that temperature, but anyway, this mobility greatly increases the probability of solvent penetration, that is. If the polymer is amorphous, but the dissolution temperature is lower than the glass transition, the rate of dissolution is lower. All right, again, the chains are frozen in the glass transition sense. Let's call it that. All right, not frozen in terms of the physics of what polymer chains are doing when the temperature is less than Tg.
So is free volume a part of this explanation?
Absolutely free volume, yeah. So you can look at it that way. So as we increase the temperature, we increase the free volume, more space for the polymer to be penetrated by those solvent molecules. All right. Free volume only truly drops to 0 at 0 degrees Kelvin. All right. So there's always space associated with the fact that you have these vibrating chains. But when it's below the glass transition, the polymer diffusion or the solvent diffusion rate is going to be relatively low compared to higher temperatures. Now, of course, there's a caveat which you guys should hopefully remember, because we just talked about it in terms of diffusion. Solvent penetration of the glassy polymer to itself lower the glass transition to the polymer. All right. So when we put a solvent in there, that solvent is going to increase the free volume in the system. So it's essentially lowering the glass transition of that polymer when the solvent is present. Okay. So if we're at the glass transition, solvent shows up, suddenly the TG is going to drop below that temperature. That's the very first thing that happens because you've added a critical increase in free volume, and now it's able to actually have exceeded the glass transition. So we create greater free volume and motion as a response to that. So this is sort of the extension of diffusion, and the fact that it self-catalyzes itself in terms of diffusion. It's doing the same thing when it comes to dissolution. When TG is decreased to around the dissolution temperature, polymer chain mobility is increased, and the rate of solvent diffusion becomes rapid because of this penetration. All right, this self-enhanced free volume. All right, so hopefully that's all relatively straightforward. And of course, this relates to the question we had earlier. When the polymer is cross-linked, the polymer cannot dissolve it. All right, it's not going to break any primary chemical bonds, but it can get in there and swell it. This is a problem with engineering nylons. So nylon is sometimes used as an engineering polymer, and one of the things they can do to it is cross-link it, but it turns out that solvents can still get in there into the nylon and swell it a little bit. And the question is that a problem for you in the application or not? So the cross-linked polymer chains cannot diffuse in the solvent, but if the solvent still penetrates it, so we start out with something that is very tightly cross-linked, and we start to add in solvent molecules into that surface, and we end up with more and more as time goes by and exposure goes by. Then we're starting to make something that is still cross-linked, by the way. The structure hasn't changed because you're not breaking those chemical bonds. You're just starting to swell the overall structure.
It seems to kind of look like plasticizers almost in the drawing sense. It looks almost like plasticizers in a sense in this case.
Yeah, I mean, it has the same effects in terms of increasing the free volume and making it easier for chains to move around each other. The limitation here is that we have these cross links, and these can be pretty far apart from each other. So there's plenty of room for solvent to go in there and interact with these regions of space where the polymer chains are not cross-linked. All right, it's just the cross-links themselves are far apart. And so if you have a solid that suddenly starts to become gelatinous at its surface, obviously load bearing is a problem in this context. And so just because it's cross-linked doesn't make it invulnerable to solvents going in and causing these levels of plasticization. If the polymer is highly crystalline and the dissolution temperature is higher than both TM and TG, solvent diffusion is rapid. Should not be a surprise. All right, lots of energy, and we think about being above the melting point. We can be above the melting point of the polymer. We do that all the time, and it's not molten. In our hands, it's still a useful plastic. Okay, but it means it's above its melting point, which means that it's more susceptible to dissolution. If it's highly crystalline and the dissolution temperature is lower than TM, all right, that's going to make things more difficult. It doesn't mean it's impossible. So, as I keep saying over and over again, we dissolve a lot of polymers in the lab. Polycaprolactone being our favorite one. Everyone loves to electrospin polycaprolactone, and it's highly crystalline. All right, and we drop it into hexafluoroisopropanol, and boom, it dissolves right away. All right. Other polymers, I think the main one we had struggles with was polysulfone, which we thought would dissolve in hexafluoroisopropanol. Turns out it doesn't so well, and so we had to mix in like 25% dichloromethane, and then it dissolves just great. All right, and then we can spin it and do all kinds of things with it. But so you play these little games. So my point being that even though it's crystalline, which PCl most certainly is, doesn't make it invulnerable to dissolution. All right, it's just a little more difficult. Solvent diffusion will be very slow, relatively speaking. Again, you put PCl into HFP and it dissolves pretty darn quickly. Takes a little time, all right, but it's not difficult at all. We do know that crystallinity decreases solubility, all based on our understanding of diffusion and the factors that work in terms of controlling diffusion. Okay, and we can't look over the rule of like dissolves like. A solvent may dissolve a polymer having similar chemical groups or similar polarity. So we talked about PVA already, OH groups. Hydrogen bonding is going to be rapid between the OH groups and water, and so it's just going to ladder that water into the polymer chain. Okay. Similarly, if we have polystyrene, shown here with all the double bonds shown, and we expose that to toluene, which is kind of a substitute for benzene. Toluene is not exactly environmentally friendly or safe either, but it's a hell of a lot better than benzene. It will dissolve in toluene. So we're going to dissolve a polar polymer. We think about polar solvents. PVC can dissolve in chloroform, which if you don't know what that is, it's the one they always talk about in the TV shows. Like you put it over your mouth and boom, you're instantly unconscious. That's the way it works in the movies. It's not a reality, fortunately. It's 3 Cls and 1 hydrogen. All right, so lots of chlorine in chloroform, meaning that it can ladder its way in using hydrogen bonding with the structures that are present inside of PVC. Nonpolar polymers typically dissolve in nonpolar solvents. Polybutadiene, all right, it's all carbon and hydrogen, can be dissolved in hexane, benzene, and toluene. We'll talk more about that in a minute, but generally that's typically true. So these are the general rules, and there are, as always, exceptions. So it turns out that this is not completely predictive. There are some polar polymers that can be dissolved in nonpolar solvents. Some nonpolar polymers can be dissolved in polar solvents. All right, there's a lot of those, actually. And polar polymer cannot dissolve in all polar solvents. For example, water. All right, PVC does not dissolve in water. All right, fortunately, because we use PVC to handle water. It'd be a problem if it could. And then a nonpolar polymer cannot dissolve in all nonpolar solvents. For example, polyethylene, which would be great if we could electrospin polyethylene. Turns out you need to, put it in hexane at 125 degrees centigrade under pressure, and then maybe it'll decide to dissolve. All right, so polyethylene turns out is a bear to dissolve in anything, pretty much. All sorts of non-polar solvents will not touch polyethylene. So, there are a lot of what-ifs under these circumstances. So those are the general rules. Okay, so that should be pretty logical. And then we start to get into the quantitative end of things. First off, are there any questions about what we just talked about before we crank into the plug and chug aspect of solubility? We're good. So, the solubility of one component in another is governed by the equation of the free energy of mixing. As in everything in material science, we always think of delta G equals minus delta H minus T delta S. And so this is our expression, except that now, in this context, M refers to mixing. All right. And so we have first off the change in Gibbs energy during the mixing process. Delta H is the change in enthalpy during the mixing process, and we sort of think of this as dissolution. All right, it's not just mixing, it's really dissolution. And then delta S sub M is the change in entropy during this mixing or this dissolution process, and there it makes a little more sense. We're providing the polymer chains with many more opportunities to assume many more configurations. So entropically, the polymer always wants to dissolve, always. All right, but what holds it back is the enthalpy side of things. So first off, if delta GM is negative, dissolution becomes feasible. We'll talk about that in a minute, but it should happen. So the solution process increases polymer chain mobility and thus increases S. Delta S is always greater than 0. All right, so T delta S is always greater than 0, and then minus T delta S is always going to be less than 0. So this component of the chain structure or component, it will always be driving the process forward. All right, trying to make delta H negative. So, unsurprisingly, the magnitude of the enthalpy of mixing is the determinative factor in trying to get to that point, trying to get the free energy to become negative and thus drive the process forward. So a positive delta H, solvent and polymer prefer their own company in that context. All right, so it would rather stay where it's at. Like I said, polyethylene is a great example. It'd be wonderful if we could figure out how to dissolve it. Polypropylene is not much better. Polyethylene is the worst. Pure materials are in a lower energy state, not the solution. Okay. A negative delta H, the solution is in the lower energy state. Specific interactions between the solvents and the polymer molecules lower their enthalpy, driving that process of dissolution forward. All right, so this all makes sense, and we'll talk about a lot of exceptions to this, but that's just a general view of how these things happen. All right, so for most cases, delta H is greater than 0, meaning that it opposes mixing. All right, so it means that enthalpy has to lose to entropy in this context. If it was all up to enthalpy, very few things would dissolve, but the entropy drives things forward for a lot of polymers. For delta H less than 0, polymer and solvent either have opposite polarities or experience favorable hydrogen bonding. For example, collagen, which as it turns out is a really important polymer for a lot of biopharmaceutical production, like all the vaccines that we all benefit from, are made using separations that are caused by electrospun or melt-spun collagen that then is used to separate the different components of the cells that are the ultimate source of these vaccines, for example. This stuff dissolves in acidic solutions, and we've done that. We've electrospun collagen in the lab from acetic acid. Works really well. All right, nice, simple system. Polyamide dissolves in dimethylformamide, which you guys probably don't know what that is, and that is just CH3, N8, CH3, no, that's H, not O. Okay, let me make sure that you don't write the wrong thing down. That's an H. All right, so dimethylformamide has the nitrogen, all right, in there. So the polyamide also has nitrogen, so the like dissolves like rule works pretty well in that context. And we use DMF a lot in the lab as well, so it's a pretty handy solvent for a lot of different things. So for regular solutions, we can think about this rather than the kind of artsy likes dissolve like approach, using the Hildebrand equation or Hildebrand and Scott equation, depending on where you went to school, apparently. Delta H equals V sub m, which is the total volume of the mixture, times the quantity E minus V sub 1 to the 1/2 minus E2 to V2 to the 1/2. 1 is the solvent, 2 is the polymer, and then these new 1, new 2. So the delta E is the energy of vaporization to a gas at 0 atmospheres pressure. Capital V is the molar volume of the components 1 and 2. Again, 1 is the solvent, 2 is the polymer. Volume fraction of the solvents 1 and 2 in the mixture, so you have to keep track of this going forward. Delta E divided by V is the energy of vaporization per unit volume, and this is something called the cohesive energy density, which we talked about briefly way back at the beginning in terms of how easily you can pull these polymer chains apart. So that kind of makes some sense in this context, because the same thing's happening here, except the solvent's doing the work. Measuring the strength of intermolecular interactions. Usually component 1 is the solvent, component 2 is the polymer or the solute involved here. So we have this big ugly equation which likes. And so what we do is define a very nice shortcut. Lowercase delta is equal to the quantity delta E divided by V to the 1/2. This is called the solubility parameter. And as you'll see, we can look these up, which is where you'll experience them is looking them up or doing some simple calculations of them. And so that takes this nasty looking equation for the enthalpy of mixing and simplifies it to this V sub m times the quantity delta 1 minus delta 2 squared times nu 1 nu 2. Delta H sub m is always going to be greater than 0. However, if delta 1 and delta 2 are same or close, that means that the delta mixing is equal to or close to 0, and this may, of course, depending on S, result in this delta G less than 0, and the process of dissolution would then be enabled in that context. So, like still dissolves like to some extent infers that the solvent and the polymer have similar deltas. All right, so what we're shooting for is for this to be 0. All right, so delta 1 and delta 2, the difference between them should be small, and then we're likely to get dissolution. Okay? This provides a quantitative basis for understanding why some solvents can dissolve a polymer and why some others cannot. Now, I wish I could tell you it was 100% predictable, and in many cases it is, in some cases it isn't. All right, we'll talk about those as well, but it is what it is, and it can be useful. And so I said there was a table, and here's the table. And so we have, for a whole bunch of different solvents, we have deltas. This calories per cubic centimeter to the 1/2 seems to be the preferred unit. I'd rather they use megapascals to the 1/2 because I like megapascals to the 1/2. Calories per cubic centimeter to the 1/2 sounds like a 1950s unit to me, but anyway, a lot of people use that. So that's typically what we're going to be talking about, in the context of this class. Hydrogen bonding refers to how strongly the hydrogen bond. All right, so we have poor, medium, strong in the context of bonding. All right, not that that matters that much, but it should make some sense. And we also have to think about specific gravity for some of the equations that are coming up. So this density factor is going to be significant for you. So don't be surprised to see that again. All of these parameters can be used in these equations. These are for the solvents, by the way. The same type of thing for the polymers as well. And so a lot of which we just talked about: polybutadiene, polymethylene, polymethyl methacrylate, PTFE, polyisobene, polystyrene, cellulose again, different versions, the nylons, polyethylene oxide, PET, and both crystalline and amorphous. And you can see that those values for delta are the same. However, the densities are different, and that's where the density can be used to determine whether or not we get solubility. Polyvinyl alcohol and polyvinyl chloride, all of which we've been talking about over and over and over again. And again, the densities will become significant. Okay, so I would give you these tables on a test. All right. Don't need to memorize, but you should be able to work with them. So, the greatest tendency of a polymer to dissolve occurs when its solubility parameter matches that of the solvent. So the delta of the two deltas is 0, essentially. That's what we're looking for. And that's what drives the process forward. And over time, it's been observed that the polymers will dissolve in solvents having solubility parameters within approximately 1 unit of their own in terms of this calories per centimeter squared to the 1/2. And in many cases, you like the difference to be around 0.1. Some people say it's around 0.5. It's kind of a wash because there's so many exceptions that I don't think it really matters that much. But if they get close, that suggests that they should dissolve. Those values should be small. So we look at methanol in water. Will it dissolve polybutadiene? Methanol is 14.5. Water is 23.4. Polybutadiene is 8.4. Fortunately, no. Our tires do not dissolve when we drive in the rain. So that's a good thing in this context. All right, but even alcohols won't affect tires, which is a nice bonus because there's all sorts of organics out there in the real world. However, if we have toluene and xylene, those will both attack and dissolve polybutadiene. Fortunately, we don't see those on the road surface, or we'd have a very different driving experience. And yeah, those are both carcinogenic, so that would all be triply bad. And then benzene will also dissolve it. Now, I would point out that benzene is 9.2 and polybutadiene is 8.4, so it's a little bit above 0.5. All right, but in general, it will affect rubber. Of course, it might have to do with cross-linking, molecular weight. All those things can play a significant role, but please don't drive through benzene if you ever see any. It would be bad. And then, maybe more familiar, can water and methanol dissolve polystyrene? Methanol is 14.5, water is 23.4, polystyrene itself is 9.1. Absolutely not, which is good because we rely on polystyrene to contain water all the time. And that's not unusual for us. And if we look at the combination of benzene, toluene, and xylene, benzene is 9.2, toluene is 8.9, xylene is 8.8, polystyrene is 9.1. They will all affect polystyrene. Acetone, on the other hand, is 9.9, and again, this is significantly different from 9.1, but in reality, acetone can pretty darn quickly dissolve polystyrene. Right. So again, these are guidelines, not necessarily hard and fast rules. But I would ask you to predict that based on this 0.1 or 0.5 ratio. I wouldn't expect you to know these things off the top of your head. And then, an important question, can water dissolve polyethylene oxide? Water is 23.4, polyethylene oxide is 9.9, and again, you don't know the structure, or if you do, that's great. And that is the repeat unit of polyethylene oxide. It's a very popular polymer in my line of work because you can dissolve this in water and electrospin it out of water. So if you go into a high school and you want to demonstrate electrospinning, you dissolve some PEO in water and you can spin it, all right, without having to worry about fume hoods and all that stuff. So that's a handy thing to be able to do. And so it should make some sense looking at that structure that water can hydrogen bond with that oxygen pretty easily. All right, so again, it's going to just ladder its way into the structure. Yes?
You were asked a question like that on the test, and it's like an exception. You draw the structure first.
If I ask a question like that, would I draw the structure for you? I'd ask you to calculate it. I wouldn't ask you to look at a structure and predict anything. If I give you a polymer that you're not familiar with, I'll show you the polymer structure. Don't worry about that. Same holds true for solvents as well. But in general, at this point, we're in kind of the plug and chug mode as far as these problems are concerned. All right, so in reality, it is, even though theoretically it shouldn't. Polyethylene is highly water soluble. Polyethylene oxide, is highly water soluble in water. Better is acetone at 9.9, so those guys are closely matched. Benzene, toluene, and xylene, which you saw up here, those will also dissolve this 9.9 material as well. All right, so lots of things dissolve polyethylene oxide to varying degrees and speeds, of course, but they will dissolve it. And then we talked about many times now, polygonal alcohol, which is that series of OH groups on the carbon-carbon chain. Water, again, 23.4. PVA is 12.6. Shouldn't dissolve it at all. Theoretically, it's way off. In reality, however, it is water soluble. Okay. And as I mentioned before, you might have to try a little harder. You might have to heat it up. You might have to wait overnight. But eventually, it should dissolve the PVA. But if it's really high molecular weight PVA, you're going to have to work harder to make that process happen. Can acetone 9.9, benzene 9.2, toluene 8.9 dissolve polyvinyl chloride, which is an important question. Yes, it can. So it's a good thing we don't have these solvents going through polyvinyl chloride pipes. That would be a particularly bad thing to do, along with the fact that it would dissolve the DEHP really quickly as well. All right. So we don't use PVC when we work with those solvents, or chemical industry doesn't use PVC when they work with those solvents. All right, any questions about it? Should be pretty straight. Yes?
Will we need to know these exceptions, or will we just need to be able to calculate the 0.1 or 0.5?
You just need to be able to calculate the differences. Yeah, you don't need to know things a priori. I'm telling you what happens in the real world, but on a test question, I'll just say, predict this. All right. You don't have to have all the exceptions memorized. Don't worry about that. Okay, any other questions about that? All right, and so that was pretty straightforward, and this is another way of doing the same thing, meaning that I can either provide you with the deltas for the polymer solvent combinations, or I could ask you to calculate it based on the structures that are present. And this is kind of gets into the like dissolves like regime. Maybe not as obviously as that, but it starts to move in that direction. And this is driven by the fact that solubility parameters can be calculated based on knowledge of the chemical structure of any compound, polymer or otherwise, by looking at the density of that polymer or solvent times the summation of all the different groups that make up that polymer, in most cases is what we're talking about, divided by the molecular weight of the repeat unit. So that's something that you should have familiarity with calculation of by looking at the structure. And so what we have are these tables, which you have to kind of be familiar with somewhat. And this is driven by the fact that it's a table, and it's not easy to represent all the information that you want in a table because it's only able to work with what you can type. And so that's what's shown here. So we have CH3, we have CH2. So the CH3 might terminate a polyethylene chain. The CH2 is in the middle of the polyethylene chain. And then as we'll see, you can have 3 bonds to the carbon, leaving 1 hydrogen behind. That's what that little less than or greater than sign is supposed to show. Okay? And then immediately below that, you have 4 bonds to the carbon with no hydrogens on it. Okay? You see what they're doing there?
Can you say that again? What is that?
Yeah, so these are it's a way of trying to show something from a typewriter that is kind of three-dimensional. So this is CH3, so the end of a polymer chain like polyethylene, and CH2, the middle of the polyethylene, and then this is 3 bonds to carbon, leaving 1 hydrogen behind to bond to that carbon, and then this is 4 bonds to carbon. All right, no hydrogens at all. All right, and then we go further. We use an equal sign to indicate a double bond, and then this is a double bond with a single bond to that carbon, and this is 2 single bonds and 1 double bond to a carbon. All right, and what we're doing is we're picking out these values for those different groups based on the bonding that's present in those structures. Okay? So I'll give you a couple of examples. Multiply that by the density and divide by the molecular weight of those repeat units. All right. So a lot of minor stuff. So what I'm going to do is I'm going to put homework on the website, and you guys can turn that in on test day, and it'll be a completion grade. All right. So if you don't do a great job, I'm not going to grade you for that, but just complete it. All right. And I suggest that you can do a great job of completing it because you'll see the same types of problems on the test. So we're going to calculate the solubility parameter of polystyrene, and we can take that polystyrene and divide it up. So we have CH2, CH2, we have CH, we have CH, and then we have the phenyl group and the phenyl group. And what we do is we go to the table and we look those guys up. So we look up CH2, get out of the way please, CH2, so this guy is a CH2, meaning that it contributes 133, and then we have this guy CH, meaning it contributes 28, and then we have the phenyl group, which, make sure I get this right because sometimes it's a little tricky. Well, for right now, we'll just go ahead and... 735. Yeah, we're going to go with that, but I think there's another variable. Right now, we'll just go with phenyl meaning 735. There's a phenylene issue that can show up. That's what I'm thinking about. So, but right now we'll just go with that. So those would be the contributions that we'd have to sum up, all right? And then that guy has one bond. That's phenyl.
Gotcha.
Okay. Solubility parameter of polymethyl methacrylate, which you guys are just vaguely familiar with at this point. Carbon, 4 bonds on it right there in the middle. And then CH3, and then we have a carbon that is an ester group, meaning you've got a double bond and the single ether bond, that's COO. I'm running out of colors. That guy, and then going all the way back around, CH3. And these are those guys are actually the same thing. All right, just counting them all up in this context. All right, and so looking at the table, then you should be able to pull out the fact that for CH2 it's 133. For the carbon with 4 bonds, it's minus 93. All right, so there are minus values in this table. CH3 is 214, and the ester bonded carbon is 310. So you sum all those up based on how many of them there are, multiply by the density, divide by the molecular weight, and you can get delta. All right. Again, I would give you these tables. Please don't memorize them. I don't know why you'd want to, but you don't have to. Any questions about that? Yes?
So the question will be, we'll just have to figure out how to break this polymer chain down, right?
Yeah, how to break.
Part.
Yeah, break the monomeric unit down in the polymer chain. Yeah. Yes.
That L is the same as the one from the tables earlier. That is the cal per second.
I hardly heard any of that at all. What did you say, please?
So that del that's calculated is the same one that's up here as the calories per centimeter cube?
It's supposed to be.
Okay.
Okay, it's supposed to be. Example. Any other questions? All right, so polybutadiene. Again, we can divide it up into CH2. There's 2 of them. All right, and then the carbon doubly bonded and a single bond. And so there's, let me change colors. There's 2 of those. And so we have 133 and 111. But you sum them all. So there's 2 of each in this context. You can't just pull out one number. You have to pull out all 4 numbers based on the information that's in this table. All right? Not really that difficult, but becoming familiar with finding the group in the table and using that information is something that's important. Back up to the other. And then last but not least, now let me say amorphous PET. There's reasons for that because these calculations, these tables refer to amorphous structures where the crystallinity is not a barrier. All right, in this context, and sometimes PET is deliberately made crystalline, at least weakly crystalline. And so we can take this based on the structures where we have the carbon, and now the tricky part, as I was worried about before, is the phenylene group is 658 in this context. And so it's phenylene, not phenyl. All right, so those are 2 different things. The previous one showed you the phenyl. This is phenylene. Okay, so keep that in mind. And then we have these CH2 groups in there. And that should be it. That's everything you need to turn around and calculate the delta for these given polymers. All right. So I would ask you to predict whether this solvent dissolves this polymer based on information in these tables. I wouldn't ask you to have any prior foreknowledge or a priori experience with polymers at all, so don't worry about that. Yes?
So how do we know the difference between phenyl and phenylene?
Okay, so the phenylene has those 2 bonds to the phenyl group, all right? That's a good question. Any other questions? Yes?
For the ones that have a range, how do you know what value to use? For a 5-membered ring, it's 105.
I'm not going to give you that problem. Don't worry about that. Yeah. If I did, I'd say just take the middle. But I'm not going to. Any other questions? All right. If not, I will see you guys on Wednesday. Our test is when?
Week from Wednesday.
A week from Wednesday. Not sooner, not later. All right.